Hi, so today we're going to be looking at Legendre's differential equation, and well, this is the differential equation we're going to be solving. These, as always, are the properties we're going to be needing or previous results. So really fast, I'm going to make a quick introduction, but before all of that, well, this equation actually appears in many areas of physics. For example, in electromagnetism, when we solve Laplace's differential equation in spherical coordinates with axial symmetry, you have a video on it on my channel. We will get to this equation and we will need to know what the result of this equation is. So, well, here we will look at how we can actually find this result. So, well, first of all, we need to know what the gamma function is, and really quickly, it is a generalization of the factorial. Not gonna get into too much detail here, but, well, this is the integral definition, and it is defined for x greater or equal than 0. Also, we can extend it to x belonging to the real numbers except the negative integers, like -1, -2, or so on. Also, it cannot be defined for 0, because the function diverges. So, well. Now, some properties that we will need is, well, that gamma of n for positive integers, like 1, 2, 3, or so on, is actually n minus 1 factorial. Also, gamma of x plus 1 is equal to x times gamma of x for x being positive, or x belonging to this set that I said, which is a more extended set. From this property, applying it repeatedly, we get to this relation, where, well, so we see this is a product. Let me just do this real quick. This product notation just means that we have x plus k, and this is, well, for 0 we have x, for 1 we have x plus 1, and so on, we have x plus m minus 1. So this product can be expressed in terms of the gamma function, like follows. Well, we have the gamma function evaluated at x plus m. We need that this inside, this part that is evaluated at belongs to this set of numbers, as we said. Also, we have gamma of x, so x has to belong to this set of numbers too. Well, this works for m equals to 1, 2, 3, or so on. We will prove this in other videos and talk more about it, but for now, we will just use this result. Now, the Frobenius method is what we are actually going to be using for solving this differential equation. And, well, it just tells us that we have this kind of differential equation. Well, we can call x naught an ordinary point if this holds. If p of x naught is not 0, in that case, we can propose this kind of solution, a solution which has an expansion, an infinite series expansion. So, well, yeah, that's all we need to talk for now, but well, just really quick, x naught is the point around which we are evaluating this sum. And we'll see afterwards how we can get the radius of convergence for this infinite series. If you want to know more about this Frobenius method, just look into my channel. I will be uploading videos talking about it. And well, this is another relation we're gonna need, and it is just another expression for the factorial. 2n factorial can be expressed as follows, and 2n plus 1 factorial can be expressed like this. If you don't believe me, just try it out for yourself and you see that this relation holds. Now we are ready to talk about this differential equation. And well, this differential equation can be solved with the Frobenius method, but as we said, we need some point around which to expand it. So we're going to be choosing that x naught is 0. And how do we know this is an ordinary point? That is, that px naught is not 0. That's what we mean by an ordinary point. Well, let's just check. In this case, px is just 1 minus x squared, right? It is the part that is multiplying y double prime. Px naught, in this case, is just, well, this evaluated at 0, which is 1. And this is not 0, so, oh, okay, x naught is an ordinary point. I don't know why I did that, but an ordinary point. So we can propose this kind of solution. Now, what is the radius of convergence? That is the region at which this is valid. Well, all we have to do is to see, okay, well, at what points does p of x become 0? Let's just impose this. Well, this only happens for x equals to plus or minus 1. So if we draw here the complex plane, we have the real part of C and the imaginary part of C. Let me just call this X. Well, what is the point we're expanding? We are expanding around 0, x0. And what are these 2 points? The points at which this function goes to 0. Well, those points are +1 and -1. So if we draw this kind of circle right here, this is the region in the complex plane where this series will be valid, will converge to the solution. So in all of this is where our result is valid. What is the radius of convergence length? It is just this distance. Well, it is the same as this distance, so it is 1. So this is the solution will be valid for x in -1 and 1. Okay, it actually is valid for complex numbers belonging to this space, but let's just focus on the real numbers, okay? We are using this solution for x is going from -1 to +1. So let me just put that here. X belongs to -1 and 1. We notice that we're not choosing the closed interval because we don't know right now exactly what happens at this disk, right, at the outer part of our circumference. But let's not worry too much about it. It's not too important for our purposes here. So we're going to be choosing this expansion, right, around x0 in this region. So let me just real quick before actually starting to solve this equation, we need to talk about alpha. Alpha is the parameter in this differential equation. So this differential equation is defined with a parameter. And notice that this parameter is greater or equal than -1. We have chosen it like that. But by making the change of variables, beta equals to, what do we, minus alpha plus 1, we get that the differential equation becomes 1 minus x squared y double prime minus 2x y prime. Well, what is beta? Beta is just minus alpha plus 1. What is alpha? I mean, alpha here is just negative beta plus 1. So we have alpha is minus beta plus 1 times alpha plus 1. Alpha plus 1 is just minus beta. So minus beta. And this is equal to 0. Now just notice that this differential equation is for alpha is greater or equal than -1. But what happens for alpha is less or equal than -1? Well, in that case, we make this change of variables. So just notice here that alpha is less or equal than -1. But this just means that, well, alpha is just this. So negative beta plus 1 is less or equal than -1. And this just means that beta, well, -1 goes to the other side, adding minus beta is less or equal than 0, multiplying by -1 on both sides, we get that beta is greater or equal than 0. So this differential equation, well, let's just write it like this, just becomes this, plus beta plus 1, y equals 0. And this holds for beta is greater or equal than 0. This is exactly the same as this differential equation, but we have changed the parameter here. Our previous parameter was alpha greater or equal than -1, and our new parameter is beta greater or equal than 0. And this is, we can actually just say beta greater or equal than -1, because if this holds, well, this also holds. So we have the exact same thing, but with beta instead of alpha. So all we have to do is find this solution, and to find the solution in this case for alpha less or equal than -1, all we have to do is get the solution from here, put it here, and change our alpha for beta. And we would be done. So we will have our solutions for all of alpha belonging to real numbers. So that's it. So that's how you can extend it to alpha belonging to real numbers. Now, now we can actually start solving this equation. How do we do it? Well, this chalk so good. We're gonna say that the solution has this form because we already checked that x naught, which is 0, is an ordinary point. So y of x can be expressed as this infinite sum. Sum going from n equals 0 to positive infinity of an xn. Now, we want to find an. We know everything about the solution except this term. We don't know what an is. So to find it, let's just impose that it's a solution. That is, we're going to substitute into the equation. How? Well, we need y prime. And I'm not going to be proving it here, but a property of this kind of solutions is that we can take the derivative inside. So, y prime of x, y prime of x is the same as, well, the sum of the derivative of this inside function with respect to x. So this would just be an times n x n minus 1, right? It's just the derivative of a monomial. Now, what do? We take the derivative once again, and we get y double prime of x is just the sum from n equals 0 to positive infinity of, well, an times n minus 1, n minus 1 times x n minus 2. And this will be it. All we have to do now is substitute into the equation. And well, we have 1 minus x squared times y double prime. What is y double prime? As we said, y double prime is just this sum right here. Yes, an. Let's write n times minus 1 x to the n minus 2. Just notice that before writing the rest of the terms, we can expand this, multiply this by 1, we get the same sum, and multiply this by negative x squared. Let me just do it right here. So we multiply by, let me just write here. So this comes from multiplying by 1, and this new term comes from multiplying by x squared. So yeah, let me just write x squared, and again, the same sum. From n equals 0 to positive infinity of, an n minus 1 x n minus 2. And a property that we can use for this kind of sums is that we can take the x inside, because all that is varying in the sum is n. So x is like a constant in the sum, so we can take it inside. We take it inside. X squared times this is just, we add a 2 here, and we get x to the n. Why are we doing this? Well, you see afterwards why, because it's really useful to express it in these terms. So all of this, notice, is just this part. What is next is just, minus 2x and y prime. Y prime, we have it right there, is n equals 0 to positive infinity of an n x n minus 1. Again, the x can go inside, and this x n minus 1 becomes axn. Becomes xn. Lastly, alpha times alpha plus 1. We can actually take it inside the sum again, and just write, alpha plus 1 times an times x to the n. And that's it. Now, we are assuming that all of these series converge. What this means is that we can add all of these series. But for now, we are going to add just this series, and this series. Why? Well, because they have the same, the same limits, right? So we can add this series. And because they converge, they will give us the same answer, so we can actually do it. So what we will write now is, the first sum, this one, we're not going to be adding it just now. We could, but it's not going to be too useful. So we have this, and n plus minus 1. and x to the n minus 2. Just notice that all of them have an and x to the n, but this one is a bit odd because it has x to the n minus 2. So maybe we can do something here that will help us. And we'll see afterwards what it is. And now this other sum, which is just the sum of all of the terms inside. So this plus this plus this. Just notice that all of them have an, and xn. So we can actually just take all of that out. So I am actually going to write this big bracket here and say, well, yes, let me just say xn goes outside, and well, this is equal to 0. And here we have, well, alpha. I don't know, let me just write an xn because it's common for all of them. So we get alpha and alpha plus 1 from this sum. Here we get minus 2n, and here we get minus n times n minus 1 times n minus 1. And well, the limits, as we said, are from 0 to positive infinity. So this is what we get. Let me just erase this real fast. I don't know why it's so dirty today. So yeah, this is what we have so far. Well, what can we do with this? Well, we can just expand this, right? Just minus 2n minus n squared minus n. Well, this is just equal to minus n squared. And well, really this is not minus n, sorry, this is plus n, minus n squared plus n. So this becomes just minus n. So really, we don't have this, but rather we have minus n squared. And yeah, let me just write this out better. So we have an xn, and this is equal to 0. So this is what we have. Another thing we can do is notice that here, well, what is the first term? The first term, n equals to 0, and 0, the first term is 0. So this would be 0 for n equals 0, plus, well, when n equals 1, this term goes to 0, so all this is just 0 from n equals 1. When n equals 2, well, we just get the same sum going from n equals 2 to positive infinity of, well, the inside, right? This is no longer 0. So this is the same as this, but this is 0, so really n can go from 2 to positive infinity and nothing changes. What we can do here is a change of index. And what I usually do to do it fast is to say, okay, I'm gonna subtract 2 here and add 2 on all the n's here. But if you don't see that clearly, let's just say that m is equal to n minus 2. This is the change of variables. Notice that when n equals 2, n goes to 0. So n equals 2. In that case, m is 0. When n goes to positive infinity, n also goes to positive infinity, so this is fine. Well, a n becomes a n plus 2. N here becomes n plus 2, and n minus 1 becomes, well, let me just write this here, n equals n plus 2. So this really just becomes, well, an is just an plus 2, n becomes n plus 2, and n minus 1 becomes n plus 1. Let me just erase this here, and likewise, xn minus 2 is just n, so we have this right here. So let me just, I want to make the handwriting a bit better. So this is what we get. Now just notice that m is just a dummy variable, that is, all we care about here are the relations between things. So instead of m, we could write n or h or whatever letter you want, as long as we change here things. So now, instead of n, m, let's just write again, let's just write n again. it makes no difference because the sum is actually going to be the same, right? Because when we end up with the sum, there are not going to be any n's or m's left. So instead of n, let's just write n, and instead of m, just n everywhere. And why does this work? If we do what I said, well, if we do what I said, we could have just done. Well, let me just do it here. This here is the same one. So if we write n equals 2 and we subtract 2 on the limits and add 2 here, notice that, well, if we subtract 2, we get 0, and if we add 2 with n plus 2, n plus 2, and n plus 1, and this should be just n, okay? So this is a little trick that I use when I want to do things fast. But if you're not comfortable with that, just make the change of variables that I said. So I'm going to erase all of this because we no longer need it. And also, you have this expression right here. So, erasing all of this, with our differential equation, just becomes this. Again, this series converges, and now they have this common term xn. So if we add them, we will get the following. We'll get that, well, the sum going from n equals to 0 to positive infinity is just, well, let me just make the brackets again, the big brackets. It's just this term, n plus 1, n plus 2, so n plus 2, n plus 1, a, n plus 2, plus all of this, plus alpha plus 1, minus n squared. This is just multiplied by xn. So this is the relation we get. And just notice that x belongs to -1 and +1, as we said before. So how does this hold? Well, this will only hold for all of x if this term right here goes to 0. That is, well, if x is 0, this will hold for whatever this is. But if x is not 0, for example, it is minus 0.5 or whatever, this will have to be 0. Otherwise, this relation will not hold. Right? This cannot be 0 if this is not 0, because x is not 0. So we get that a necessary condition for this to hold is that, well, a n plus 2 times n plus 2 n plus 1 is equal, right, to 0. Sorry, all this is equal to 0, so, well, let me just write it like this. Oh, sorry, I meant to write an right here. Right, an. That of this alpha plus 1 minus n squared times an equals to 0. This has to hold. So we have reduced this differential equation to finding this recurrence relation, solving this recurrence relation. So, well, from this, assuming that n is not 0, getting it to the other side, right, we just put it on the other side. Now, dividing by this, which is not 0, because n is not -2 or -1, and dividing by this, assuming that an in general is not 0, we get that an plus 2 over an is equal to, well, minus alpha plus 1 minus n squared over n plus 2 n plus 1. And, well, is it okay? Yes, so let me just erase all of this again. Okay, and this. We have reduced our differential equation to a difference equation. And what is a difference equation? Well, here you can think of an as the function and an plus 2 as the double derivative. So this is what we call a recurrence relation, or as many authors call it, a recurrence relation. Some authors make some distinctions between recurrence relations and difference equations, but essentially in most cases they are the same. So this is what's called a difference equation. How do we solve it? It's really similar to a differential equation, but the methods are different because this is a discrete amount, right? It's an, a naught, a1, a2, or so on. How do we solve it? Well, first of all, let's just transform the numerator. This can be rewritten as a squared plus alpha, so, sorry, alpha squared plus alpha, so just say alpha squared plus alpha. A really nice way to do this, to rewrite this, is to write it as two things that are multiplying each other. So alpha squared minus n squared plus alpha minus n, we can rewrite this well, having into account that this term can be expanded as alpha plus n, alpha minus n, plus alpha minus n. See? We can take out alpha minus n from both sides and get alpha minus n times alpha plus n plus 1. Now, there's a negative sign here, so if we multiply by a negative sign, we get n minus alpha. So really, this and this give rise to the following term: n minus alpha and n plus alpha plus 1. This is what we get. And this is the relation we have to solve. And to not get too much space here, I will write this right here. So let me just rewrite it as an plus 2 over an, and this is equal to n minus alpha, n plus alpha plus 1 over n plus 2, n plus 1. This is what we have to solve. And let me just make sure I wrote it, okay? Yes. So this is what we have. Let me just use the other one. How do we solve it? Well, we have to notice one thing. Here, we have an and an plus 2. So really, we start with a 0. This will give us a 2. And if we start with a 2, that will give us a 4, and so on. If we start with a 1, this relation will give us the value of a 3. Likewise, starting with a 3, we'll get a 5, so we get this. So we can separate this into n odd, which is just the same as saying, well, n is equal to 2n plus 1 for n equals, sorry, this is even. I'm so sorry. It's even, and this is n odd. So n is just 2n plus 1. This is just 2n. Okay, so let me explain this. A naught, a 2, and so on. A n becomes a 2n. For m equals 0, which will be n0, m equals 1, 2, and so on. Here, well, n is odd, so we can rewrite it as n equals 2n plus 1, where m is 0, which corresponds to a1, n is 1, which corresponds to a3, and so on. So we'll separate this into two terms, the even terms and the odd terms. But apart from that, we will also need to make some distinctions afterwards, but we'll see how. So first of all, let's start with the even part. So right here, let me just write n is even. And well, if n is even, as we said, we can rewrite it as 2m, where m goes from 0 to infinity, well, it is a positive integer. Well, in this case, we can rewrite this recurrence relation as a, well, n is just 2m plus 2 over a over 2m equals to 2m minus alpha and 2m plus alpha plus 1 over 2m plus 2, 2m plus 1. This is what we have to solve. Okay? How to solve it? Well, a really nice way to solve this kind of recurrence relations is to use the product operator. That is this operator right here, the one we talked about. So if we take the product on both sides, we'll see that everything cancels out really nicely. So what do I mean with this? Well, let's just say that we take the product from, I don't know, k. Well, no, m is going from 0 to, well, let me just say k, okay? Let's just change the index from k to n minus 1 of this. Well, because we are changing our, because we are changing k instead of n, let's just, again, this is a dummy variable, so let's just call it k. So let's just write instead a over 2k plus 2 over a over 2k. And we are going up to m minus 1. Why? Because we're going to be multiplying m terms. So from 0, 1, 2, and so on, there are m terms, right? 1 is 1, 2 terms. In 2 we have 1, 2, 3 terms. In n we have 1, 2, 3, so on, m terms. So we're multiplying m terms. Likewise, if we take the product on one side, we need to take it on the other side too. So this would be the product going from 0 to n minus 1 of all of this, which is just 2m minus alpha and 2m plus alpha plus 1 over what? Over 2m plus 2 plus, 2m plus 2, 2m plus 1. How do we do this? Well, the property of this, before of that, this is a telescoping product, like a telescoping series. Why? Well, let me just expand this. So at k equals 0, we get a naught, and up we get a 2. Next term, a 2, so right, k is equal to 1, and next term is a 4. Here we get k equals 2, a 4. And lastly, upwards we get a 6. And we keep doing this, we get that the last term is, well, 2m minus 1 plus 2 is just 2m, so we get a 2m. And on the bottom, we get 2m minus 1. So this is what we get. But notice that this and this cancel out, this and this cancel out, this cancels out with the next one, and this right here, the previous term, cancels out with this one. So we're just left with a 2m over a naught. So let me just write this here. Oh, let me just erase this. So this is just a 2m over a naught. Okay. So let me just erase this. And well, what is a naught? A naught really is an arbitrary number. If we choose a naught as we want, of course it cannot be 0 as we said earlier, right? Because here, well, a n is not 0 for any n. Okay, this is what we are assuming. If a n is 0, well, this is just 0. The answer would be 0, and it's a trivial answer. So this is what we're assuming. Yeah, so that's it. A0 is an arbitrary constant, and from A0 we can get all the other even terms. How do we solve this? Well, let me just write for later this relation right here, okay? So even, and even, what we get is a to m over a naught is equal to product from k equals 0 to m minus 1 of 2m minus a alpha, and 2m plus alpha plus 1. And you see afterwards why I'm writing it like this. I'm writing it there, because I wanted to remember it. So this, okay, this is what we get. To evaluate this product, we are going to use the properties of this product. And the properties are that, well, just say that, imagine that I multiply B, C, D, E, and so on. Well, I can express this as the product of something. Of, let me just say, Bn over Cn. Okay, and this is the product. But I can express this as the product of Bn over the product of Cn, right? Because it's just the same. We get here all the terms in the numerator, and on the denominator we get all the other terms. So this property holds. What we can do here is to take the product on the numerator and the denominator. And that is precisely what we are going to do. So let me just do this again. So here we get the product from k equals 0 to n minus 1. And on the denominator, we do the same. Product from k equals 0 to n minus 1. Notice, well, this is really bad written. So, what is this? As we said before, we're going to use this identity. And this is just 2m factorial. So, this is 2m factorial. Why is it 2m factorial? Just try it out. Just for k equals 0, we get 2 times 1 times, well, for k equals 1, we get 4 times 3 times so on, and for n, k equals n minus 1, we get 2m, yes, 2m times 2n minus 1. And this is just 2n factorial. Okay, just reorganizing 1 times 2, 3 times 4, so on, 2n minus 1 times 2n. This is 2n factorial. So that's it. Now, the interesting thing is, what do we do with the product on the numerator? So let me just use this. Well, what we can do is to use this important property right here. So let me use, again, we can partition this into two products. The first product is going to be the product on the left of 2m minus alpha. We can factor out the 2, and if we factor out the 2, we get that, well, factoring out the 2 is just multiplying by 2, but dividing everything by 2, right? Because this is just 1. So we get this. 2 times m minus alpha over 2. So m minus alpha over 2. Just want you to notice that there are, as I said, m terms. So there are 2 multiplying m times. So 2 times the first term, times 2 times the second term, and so on, 2 times the last term. So there are m of them. So we can take it out and say, well, this really is nothing but 2 raised to the nth power of this product. Of m minus alpha over 2. What is this product? Well, let me just say that we can use this property right here. In this case, instead of sorry, this should be a k. It should be a k. Don't get mistaken here. This is a k, this is a k, this is a k, this is a k, and this is a k. I forgot to change the index, okay, but it doesn't matter, it's just a k. So this, in this case, is the same as this. But notice that we have to call x equals to alpha over 2. So here, we do that. well, we get 2 to the nth power times gamma of x plus m. But where is m right here? Sorry, yes, m, is m, sorry. M over gamma of x. But what is x? X is just alpha minus alpha over 2. So minus alpha over 2 minus alpha over 2. This would be our solution to this first multiplication. But notice that we have put a restriction. Whenever we apply the gamma function, we are assuming that m minus alpha over 2 belongs to the real numbers except minus 2, minus 1, 0, and so on, as we said before. Likewise, we have gamma of minus alpha over 2, so minus alpha over 2 has also to belong to this set of numbers. Minus 1, 0. What does this mean? This means that we are assuming that minus alpha over 2 is not an integer, a negative integer or 0. So let me just write this here, that for the even part, if alpha is not, does not belong to, I don't know, to negative 2, negative 1, or 0, then we can use this solution. So in that case, we can substitute this first multiplication by that expression, which is just 2m gamma of m minus alpha over 2 over gamma of minus alpha over 2. All of this makes sense because minus alpha over 2 is not in this set of numbers. Yes, that's right. Okay, let me just check. Yes, okay, so that's what we get. Now for this second multiplication, right, we have to write our pi here. Well, we'll just erase all of this again and do the same procedure. So instead of 2k minus alpha, yes, it's fast, we get, well, what do we get? We get 2k plus alpha plus 1. What can we do right here? We will also factor out a 2. But why are we factoring out a 2 all these times? Well, because in this relation, we don't have a 2k. We have a k, so we need a k on the multiplication. So taking a 2 outside, we get this. 2 times, well, dividing everything by 2 just means k plus alpha plus 1 over 2. So this is it. Again, 2 comes out of the product as 2m, and this product is just, well, gamma of x plus m over gamma of x again. But here x is alpha plus 1 over 2. Okay? What does this mean? Again, this means that alpha plus 1 over 2 cannot be a negative integer, so, or 0, of course. So this is what we have so far. If this holds, well then all this should just be alpha plus 1 over 2. This should just be alpha plus 1 over 2. Let me just write this a bit more clean because really I am writing this really horribly. So this other one was just m of m minus alpha over 2. Okay, so what we get finally is that a 2m over a naught is just 1 over 2 factorial, 2n factorial, times, 2 raised to the nth power. No, let me just write it like this. The first one was this, x minus alpha over 2, times gamma of x plus, this is m, sorry, not x, m of n plus alpha plus 1 over 2. But notice that here we also had a 2 raised to the nth power. Of course, we can put together this 2 to the n as 2 to the n plus 2. 2 to the 2n. So this is it. Okay, sorry, I had to cut from it. So what we have so far is that, well, if n is even, we get this relation. This would be our recurrence relation solved, right? Each a to n, which is each even term, is given by this relation. But this relation is not exactly general. It is subject to these two restrictions. So what are these two restrictions really? Well, as we saw, alpha is greater or equal than -1. So the first restriction, that negative alpha is not a negative integer, just means that alpha is not even, because if alpha is even, well, we need that alpha is the positive even, right? Because all the even terms for this condition are, well, 0, 2, 4, 6, and so on, right? We don't have -2, -4, so on, because alpha is greater or equal than -1. So if alpha is even, this holds. But if this holds, then this would be even, right? Because we'll have 0, which is even, and we don't want 0 there, as we said. 2 over 2 is just 1, -1, another even number. 4, -2, another even number, so we don't want that. So really, sorry, not this. This is what we want. This relation right here just means that alpha is not even. So instead of that, we will write following, which is much more easy to understand. We say that alpha is not even. Now, what does the second restriction mean? Well, the second restriction really just means that alpha is not -1. Why? Well, let's just write it again. So, second restriction just means that alpha plus 1 over 2 is not -2, sorry, it's not, I think I'm going to stay there. What I didn't mean, what I meant was minus alpha over 2 is not -2, -1, -3, no, 0, 1. Okay, it is not any of these numbers. So that's what I meant. Now here, again, we don't want it to be any of these numbers. How can we get any of those numbers? Well, really, because alpha is greater or equal than -1, this will only happen if this is an integer. When is this an integer? Well, this is an integer only if alpha plus 1 is even, because even over 2 is an integer. Alpha plus 2 plus 1 is even if alpha is odd. So alpha odd are really just, well, if alpha is odd, well, these numbers are just -1, 1, 3, 5, and so on. But notice that the only conflict point here is -1, because alpha is -1, this would be 0, which is not what we want. So alpha is also not -1. These are our restrictions for this to work. But why does 1, 3, 5 or so work? Well, because if we get 1, we get 1 plus 1 is 2 over 2 is just 1. It does not belong to these numbers. It is a positive integer, and positive integers are good, are actually really good for us. So with 3 it happens the same. We get 2 here, and 2 is not in this set of numbers, so we do not care about that. So all the restrictions that we need for this solution to work are that, well, alpha is not even, and alpha is not negative 1. This is all we need. So this is one of the reasons that we chose alpha greater or equal than negative 1, such that we have these restrictions easier. So if this is the case, we get that the solution to the recurrence relation is, well, let me just write this here because this is like inside a condition. A naught of 2 to the 2m to m over 2m factorial over these gamma function terms. Okay, so it is gamma of m minus alpha over 2 and gamma of m plus alpha plus 1 over 2. I hope that you can see it well. I'll write it better afterwards. I don't have too much space here. So let me just plus 1 over 2. I hope you can understand it well. Okay, you have too much space. So well. So let me just check, and yes, this should be. So that's it for n is even. Well, it's not really it for n is even, because what happens if alpha is even? Well, if alpha is even or alpha is negative 1, what we get is that, well, the only thing that happens here now is that we can no longer use the gamma function. In that case, we can actually just leave it as the recurrence relation. So what we had was that a to m over a naught was equal, well, to the product, right? And this product is just that, substituting again just 2m minus alpha, 2m plus 1 plus alpha, over 2m plus 2, 2m plus 1. If we no longer use the gamma function, we don't even need any restrictions for alpha. So all we have to do is to evaluate this product. Really, we can leave the product like that, but in many cases, people want to expand it. So let's just expand it and see how it looks like. But well, again, we can partition this into the numerator and denominator. This is, we said, 2m factorial. So let me just erase this and write it like that. 1 over 2m factorial times this product. Now what do we have? We have 2k minus alpha. Notice that again I'm using the k instead of m, so the summation productation, if you want to call it like that, makes sense. So 2k plus 1 plus alpha. We can leave it like that, and in fact we will leave it like that, but just for the sake of it, some textbooks like to write it this way. They like to expand it. So if we expand it, we will get the following. For k equals 0, we will get minus alpha times, well, 1 plus alpha. The next term is just 2 minus alpha times 3 plus alpha. And with one going up to m minus 1, we get 2m minus 2 minus alpha times 2m minus 1 plus alpha. And we can rewrite this in a more friendly manner as, well, just put the minus alpha terms on one side and the plus alpha terms on the other side, and you get 2m minus 2 minus alpha, so on up to minus alpha, times, well, there's another term here, is 2 minus alpha and minus alpha. And this other term right here is 2m minus 1 plus alpha, so on 1 plus alpha, and yeah, that's it. So what does it mean? Well, this just means that we're starting at 2m minus 1, and we subtract all the odd terms, 2m minus 1, 2m minus 3, 2m minus 5, until we get to 1. Here, 2m minus 2, the next one will be 2m minus 4, so on until we get to 2 minus alpha, 0 minus alpha. So this divides into even and odd terms. Even and odd terms, right? This will be even and this will be odd. So what do we do now? Well, we can just leave it like that, and in fact that's what we're going to be doing. And just notice that, well, nothing, no, not really, not too important here. Yeah, just leave it like that. So the solution is a to m equals to a naught 1 over 2m factorial times this product. Well, this is just 2k minus alpha and 2k plus 1 plus alpha. Just write it well. And yeah, that would be it for the even terms. As we see, we have two solutions if n is even. The first solution is given by, let me just emphasize please, the first solution is given by this if alpha satisfies these equations, these relations, and the other one is alpha is even if it satisfies these relations. Really, this relation holds for both of them, because if alpha is none of this, well, this can be written in terms of gamma, and if alpha is just, it's just, this is the general expression, and it reduces to this if we consider this kind of alpha. Now, in many textbooks, what you will find is that they don't even consider this part right here. Oh, sorry. They don't even consider that part right there. Why? Because in reality, what you usually encounter is this part right here. You encounter that alpha is even, or really it is an integer, as we will see afterwards. So this is what you will usually encounter. So they don't even bother with this part, but well, this is a more general solution, right? Now, what do we do? Well, we just go for the odd terms, right? Don't we? So if n is odd, this just means that n can be expressed in terms like this: 2n plus 1, or n is 0, 1, 2, and so on. What do? We'll write that expression again, but we're going to put it already inside the product because we already know what we are going to be doing. So this is what we're going to be doing. Not losing any time, just going straight for the calculations. So an plus 2 over an, what is n is 2m plus 1, but instead of m, as we said, we're going to write k, so we can take the sum, or in this case the product, okay? So a over 2k plus 1 plus 2, 2k plus 3, a over 2k plus 1. Here, 2k plus 1 minus alpha, and 2k plus 2 plus alpha, and well, just like this. 2k plus 2, sorry, plus 3 here, and 2k plus 2. What do we have? Another telescoping product. Let's just write it real fast. A3, A1, A5, A3, so on, up to A2m minus 1. Sorry, 2m plus 1, and A2m minus 1. This, we get two terms, and in fact, let's just write it. We get this. Why am I leaving this space here? Well, because we already know what this quantity is, isn't it? We have it right here. If you don't believe me again, just do the calculations that you see that you get this result. So this is just 1 over 2m plus 1 factorial. And all we have to do is to calculate this product right here. So, yeah, I just do it. How do we do it? Then we gotta partition this into two products. First product is, oh, let's just do it. 2k plus 1 minus alpha, and the other one is, well, let's just do the other one afterwards. So 2k plus 1 minus alpha, we can factor out a 2. If we factor out a 2, we will get it here, and we will divide by 2. These 2 can come out, as we said before, because it is multiplying m times, and we get this product. So k plus, sorry, this should be a plus, isn't it? No, a minus, yes, a minus. K plus 1 minus alpha over 2. What do we do here? Use this relation, this wonderful, amazing relation, and we get that if we call x equals to 1 minus alpha over 2, we get 2m gamma of m plus x, which is just 1 minus alpha over 2, over gamma of 1 minus alpha over 2. So here we have n is odd, and just write it. Okay, so this stands for the first term. What are the restrictions here? Well, the restriction, again, is that n plus this is not a negative integer or 0, but it is equivalent to saying that this is not a negative integer or 0, right? Because n goes from 0 to 1, 2, 3, 4, 5, and so on. So we have that 1 minus alpha over 2 does not belong to this set of numbers. And that's the first condition. Let me just erase this. That is 2k plus 2 plus alpha. Yes, so I remember. Well, this is the first part of our result. So 2m times gamma of m plus 1 minus alpha over gamma of 1 minus alpha over 2, multiplied by this other product that I'm going to write down here, so I don't have to write so much, because it's a really long time writing. So this other product is this one right here. So capital pi from k equals 0 to m minus 1 of 2k, I think it was, yeah, it was 2k plus 2 plus alpha. Just check for a second, and yes, 2k plus 2 plus alpha. Again, multiply and divide by 2. So 2 over 2 is just, well, 2m goes outside, and this just becomes this product. K plus 2 plus alpha. And this, if we call x equals 2 plus alpha over 2, what is it? It's just, sorry, not this. It's just 2m, and using our gamma function amazing relation, m plus 2 plus alpha over 2. What are the new restriction? The new restriction is that 2 plus alpha over 2 is not in this set of numbers either. So this should be the final part of our solution. 2m times this is just becomes 2 to the 2m, or 2m squared, times this and this new factor, which is just gamma of m plus 2 plus alpha over 2. And well, once again, let me just make these conditions a bit clearer. This condition really always holds because alpha is greater or equal than -1. This means that 2 plus alpha over 2 is never in this set of numbers, right? Because the only conflict point would be alpha is not -1. So here we need, and alpha is not -1, really. If alpha, no, sorry, it doesn't even, it never holds. Sorry. Because if alpha is -1, well, this is just 1/2. If alpha is between any of those numbers, this will not be an integer, and so if alpha is, for example, 1, 2, or 3, we get positive integers, which are not there. So this really is not any restriction, this will always hold. So get rid of it, and we don't need anything else. Now, the problem is when we consider 1 minus alpha over 2. So when we consider 1 minus alpha over 2, this will only be an integer if alpha is odd. So alpha is odd. We get that, it can be -1, 1, 3, 5, and so on. If it is -1, really we have no problem because this would just be 1, right? Yes. But if it is 1, for example, here we have a problem because it will become 0. If it is 1, it will become 0. If it is 3, it will become -2. -1, sorry, -1. If it is 5, it will become -2, and so on. So these are our targets. What does this mean then? Well, if we want this to not hold, we need that alpha is not odd. So notice that this is this is analogous to this one, but the opposite, right? Here we need that alpha is not even, and here we need that alpha is not odd. So let me just write this here. Alpha is not odd. So if alpha is not odd, we get that our solution for our recurrence relation is just a2m plus 1 a1 times 2 to the 2m over 2m plus 1 factorial times this gamma function terms. So let's see if I can fit it all in here. Gamma and gamma. So it will be 1 minus alpha over 2 and 2 plus alpha over 2. So this is it. I'll write it better afterwards. Just check for a second. And this is a plus right here. Yes, so that is it. Now, what happens with the other case, the case in which alpha is odd? Well, if alpha is odd, again, we just have to write our general relation. And what is our general relation? Well, it is just that alpha 2, 2m plus 1 to no, it was 2m, yes, 2m plus 1, is equal to the first term alpha 1 times 1 over 2n plus 1 factorial. Just I'm going to do it faster, doing it fast, but if you have any doubts, just go back in the video, check the general relation, the one with the product, before we use our gamma functions, and this is just what I'm writing here. So let me just write this thing. And this product is just 2k plus 1, 2k plus 1 minus alpha, and 2k plus 2 plus alpha, from 0 to n minus 1. So that would be it. We already have our full solution ready. So for this, our general solution is given by this expression around x naught, for x belonging to -1 to +1, without including the extremals of the interval. So our solution can be written as, well, y of x is this sum right here. The sum of n equals 0 to positive infinity of an xn. What is an? Well, as we see, there are quite a few cases. We have an for n is even and an for n is odd. So we will actually divide the sum into the even and odd terms. So the sum will be, well, let me just write it like this. Let me just write it as, this function would be really 1x plus y2x. This stands for the even part and this stands for the odd part. Or maybe just, let me just write even and odd. And just have into account that we can take out the a0 and a1, but we'll see afterwards how. So well, let's just say that the even part is, well, it's given by this. Remember that if n is even, m equals 2n. So instead of n, we will write m, m equals 0, 2, 1, 2, and so on. So here we're writing a to n, x to the 2m. And this would be our even solution plus the odd part of our solution. So why have we written it like this? Well, let me just. Why have we written this like this? Well, because we see we have partitioned our general term an into a2m and a2m plus 1. So really, our an is a2m for n even and a 2n plus 1 for n odd. But there are even more restrictions, right? We need to have into account if alpha is not even, if alpha is not odd, and so on, so on, so on. So let me just do a quick, let me just think for a second how I will organize the solution. Okay, so I have already thought what the best way to present the results are, and because there are so many restrictions and conditions, I think that the best way to do it is as follows. So just notice the following. Here we have partitioned our solution into two terms, right? In general, we have an x to the n, right? But we can say that, well, an can be, n is just 0, 1, 2, 3, and so on. So we can partition an into, well, the even terms, right? A to n, which would correspond to a0, a2, a4, so on. and the odd terms, A1, A3, A5, and so on. So, assuming, well, we know that this series converges, so these two series will converge too. So this is what we get. This is a 0, okay? I don't know. It looks like 1, it's 2. So we have these two series, so we can add them and partition them. So this is the best way that we can do it. Now, we know what a to m is, and we know what a to m plus 1 is. Really, the whole video has been based on finding these two terms. But there are some restrictions. For example, a to m is different if alpha is even. Right? If alpha is even, it's just this right here, and if alpha is not even, or it is not -1, it is this here, because the gamma function works. It can be used. Now, if n is odd, likewise, we get two terms. One, depending on if alpha is odd, right? If alpha is odd, we just get that, and if alpha is not odd, we just get these terms with the gamma function. So what can we do? Well, just notice that, hey, alpha is a real number, right? Well, alpha is, let me just write like this. Alpha is greater or equal than -1. All of these numbers can be divided into, well, alpha is an integer, right? It could be -1, 0, 1, and so on. Or alpha is not an integer, that is, well, the rest of the terms, right? So here we'll consider -1, 0, 1, 2, 3, and so on. And here we'll consider the rest of all the numbers. So, in that case, in this first case, we have that we will choose this part and this part, right? Because alpha is either even or odd. And in this one, we will choose this other part, because here alpha is never even or alpha is never odd. So let me just erase this and see what I mean. So, our first part, let's say that alpha is not an integer. This would be our first part of our solution. If alpha is not an integer, then alpha cannot be even or -1, because they are integers. So we can use this solution for a to m. Likewise, it cannot be odd, so we are in this case. So our general solution could look something like this. Let me just write it. Our general solution could be, well, the sum of the even terms from m goes from 0 to positive infinity. Here we are working with a to m. What is a to m? We're here, okay? A to m, but alpha is not even or -1, so a naught, but a naught is just a constant, it can go out, but well, let's just keep it like this. A naught 2 to the 2m over 2m factorial times these gamma terms. M plus alpha plus 1 over 2, so 2 gamma alpha plus 1 over 2. This would be the even part. But now we also have the odd part. And the odd part is m equals 0 to positive infinity, right? Just remember, if n is even, m is going from 0 to infinity. And if n is odd, as happens for a to n plus 1, m is also going from 0 to positive infinity. So we get this other term. A1, 2 to the 2m over 2m plus 1 factorial of these other gamma terms. I know I'm writing it really bad, I'm just going to write it afterwards here nicely to have more space, but here's just so you can see it. So m plus 1 minus alpha over 2 gamma of m plus 2 plus alpha over 2. 1 minus alpha over 2 gamma of 2 plus alpha. And just close these brackets and this would be our general solution if alpha is not an integer. But we have not yet talked about a0 and a1. What are they? We have not put any restrictions on them other than a0 and a1 are not 0. Because if they were, well, if this was 0, we'll just end up with this. And if this was 0, we'll end up with this. And if they both are 0, then y of x is just 0. So let's just assume that it is not 0, because otherwise we'll get a trivial solution. So that's it. So in general, they are real numbers. There are no other restrictions, so a0 and a1 are real numbers. They are what we call in other differential equations or integration constants. That is, we have a second order differential equation, so our general solution will have two arbitrary real constants. Okay, they can be complex, but in this case we're working with real numbers, so they are real constants. So we can do this. We can take out a0 because it is a constant, and we can take out a1 because it is a constant. So this is where we end up. If we call all of this y1 and all of this y2, we see that our general solution is some arbitrary constant a0 times a1 plus some other arbitrary constant a1 times y1. What is this? This should be a2. Y2. This is the general solution for a second order differential equation. It is a linear combination of two linearly independent functions. And why do we know these are linearly independent? Well, because I forgot here to add 2m, and here x to m plus 1. Well, because this is an even polynomial with all of these terms right here, and this is an odd polynomial. So this is what we get. They are actually linearly independent. I'm not going to prove it here, but we'll make some videos on it. So our general solution can be written as follows. I will write it here and try to fit it all. So our solution, if alpha is not an integer, is, I'm going to try to fit it all here. It is just, well, this first term, which is just the sum of all of these. We can actually take out this term, and this term, because they don't depend on m. So we get, it's actually just a0 over gamma of minus alpha over 2, gamma of alpha plus 1 over 2 of this sum. Going from m equals 0 to positive infinity of 2 to the 2m over 2m factorial of this gamma m minus alpha and gamma of m plus alpha plus 1 over 2. And we'll, don't forget our x to the 2m. Now, if we add our second term, which stands for the odd parts, we get, well, this part right here, a1, these gamma functions, 1 minus alpha over 2, 1 minus alpha over 2, and gamma of 2 plus alpha over 2. So as you see, the expression is really long. So this equation is not exactly easy, but it takes some time to solve, of course, if you want to explain everything as I have done, and it takes a while also to write the solution. Of course, we are solving it, this is a series expansion, right? So it's a combination of polynomials, right? So this is just the rest of the expansion. So 2m over 2m plus 1 factorial, and this over gamma functions. M plus 1 minus alpha over 2, gamma of m plus 2 plus alpha over 2. So this is our general solution. Wait, let me just end up this. So, okay, let me just... I messed this up. So, okay, finally, this is a really long expression to write. This is our final expression. Let me just check I didn't do anything wrong. Yes. This is our final expression when alpha is not an integer. Really long, many gamma functions, many things, many terms, infinite terms really. So this is it. And both of these parts are linearly independent and they constitute a general solution of this differential equation if alpha is not an integer. And of course, we are, as I said, we are working with alpha greater or equal than -1 and x in this range. What happens if we consider that alpha is in fact an integer? Well, the expression is a bit shorter. There aren't any gamma functions to have into account here, but something interesting happens. So let me just see this. So I'm going to write the general solution and you see what happens if alpha is even or if alpha is odd. So our general solution in this case is, as before, well, in this case we're working here because alpha is an integer, so A naught, yes, A naught, and this sum right here. Just notice that our sum is going to have a product inside, okay? So we have 1 over 2m factorial, and m is going from 0 to positive infinity of this product. Just, actually, let me just write it a bit higher. So y of x is just a naught times this sum. Okay, and now we have to include the product. This product is just, well, the product from k 0 to m minus 1 of what? 2k minus alpha, 2k plus 1 plus alpha. So 2k minus alpha and 2k plus 1 plus alpha. Lastly, x to the 2n. So this really is just another polynomial, an even polynomial, right? Because it just constitutes even terms. Now, we have to add the odd part of the solution, corresponding to a 2n minus 1, 2n plus 1, sorry. So, we are working with this part right here. So, 1 over 2n plus 1 factorial and this product, which we cannot, as we said, write in terms of gamma functions because we will end up with some problems. But this is not how we have to be doing it so far. So, well, 2k plus 1 minus alpha and 2k plus 2 plus alpha. And this is our general solution. So let me just write this. That's it. So first solution, alpha is not an integer. We get a bunch of gamma functions. If if alpha is an integer, the solution to Legendre's differential equation is really just this. In many places, you will not see this notation right here. You will actually see the expansion. You will see 2k minus, you say minus alpha times minus alpha plus 1, minus alpha plus 3, and so on. And here you have 1 plus alpha, 3 plus alpha, and so on. But really, this is a more compact way of writing it, and I think it looks really cool to have an infinite summation, and inside that summation to have a productorial, or a product. Okay, so now that we have already seen the general solution when alpha is not an integer, and the general solution when alpha is an integer, we can actually do better. The thing is that we will consider that if alpha is an integer, we will divide it into two cases, when alpha is even and when alpha is odd. Of course, we can do this because, well, all the integers are either even or odd. So, what can we do with this? Well, just notice that if alpha is even, let me just write it like this. Alpha is even, okay? Well, this just means that alpha can be written as 2n, okay? And we are gonna consider a particular case in which it is equal to n. Okay, so we have some alpha, and it is equal to n for some, for some n equal to 0, 1, 2, or whatever. It will be equal to n at some point. So what we will have really is that n is equal to 0, 1, 2, and so on, up to alpha, and then it will keep on going. This is even. And we will say this even by writing 2n. So at that point, at the point where we get to alpha, n equals alpha, this relation will become a alpha plus 2, sorry, this should be an a, equals to, if n equals alpha, this is just 0, and we get 0 times a alpha. Assuming that a alpha is not 0 in general, so this means that, well, a alpha plus 2 is 0. So, but not only that, the next term will also be 0. Why? Well, because the next term, the next even term, will be a alpha, the next term from this, a alpha plus 2, well, the following even term will be a alpha plus 4. So a alpha plus 4 would be, well, this right here, which is not 0 really, and a alpha plus 2, which is the previous even term. What do we have? This is 0, then this will also be 0, so this is 0, and if we keep on going, we actually will get that all of the following terms are 0. So what does this mean? This means that if alpha is even, then the even terms will cancel out from a alpha. That is, we will have a naught, a2, a4, and so on up to a alpha, where alpha is even, okay? Because from this point on, we will get a alpha plus 2, the next even term, this is 0, a alpha plus 4, this is also 0, and so on and so on. So we will only get up to these terms, meaning that a to m is just a naught, well, it can be a naught, a2, or so on up to a alpha. What does this mean? This means that this part, that is the even part, doesn't actually go to infinity. N goes from 0 up to 0, 1, and to alpha over 2, really. Okay? Yes, and this makes sense because alpha is even. Yeah, sorry, I got mixed up there. Well, this makes sense because alpha is even, so it is still an integer, so the sum would make sense. But if you don't want it to read like that, just say that, well, 2m goes from 0 up to alpha. So this would be our first part course, this part just stays the same, nothing cancels out on the odd terms, but here we no longer have an infinite sum. We have a finite degree, an alpha degree polynomial. So if alpha is even, then a to m is equal to 0, to a0, a2, and up to a alpha. That's what we have. So let me just erase all of it. Oh, I did not have to erase that one. Okay. Now, of course, what's the next step? The next step is just considering that, oh, what if alpha is odd? If alpha is odd, well, there will be some point, well, let me just write it as this. There will be some point where alpha will be equal to n, again, because n is 0, 1, 2, and so on, to alpha, odd, and so on. So at that point, we will get, okay, just the same as before, a alpha plus 2. When n equals alpha, this goes to 0, and we get a alpha. So a alpha plus 2 is 0, a alpha plus 4 is 0, and so on. But in this case, alpha is odd. What does this mean? This means that the odd terms, a to m plus 1, are a1, a3, a5, up to a, let me just erase this, up to a alpha. But whenever we go beyond a alpha, this is 0, this is 0, and so on. Just remember that alpha here is odd. So this is an odd term, a over odd term, odd term, odd term, and so on. So really, what do we get from here? In this case, we get that a to n plus 1 is, well, a1, a3, and so on up to a alpha. Again, here we get an alpha plus 1th degree polynomial. Sorry, not a alpha plus 1 degree polynomial, an alpha polynomial, because this is odd. Okay? So in both cases, here we'll get that this term is finite, and this is an infinite series, and for this term we get that this is an infinite series, but this becomes finite. So for you to see it really clearly, I'm going to erase all of this and write the solutions here so you can understand them really quickly and see them really fast. So just give me a minute to erase all this and write the solutions. Okay, so we have finally reached the general solution. And well, the general solution is this that I have written here. And as you may see, it actually has different forms for different values of alpha, and they are quite long. So let me just break it down for a minute, and then I'll just leave you with the whole answer. So first of all, we started with the Legendre differential equation. Well, this is a second order differential equation, and it depends on this parameter, which we have assumed that it is greater or equal than -1. In the case that you want to calculate it for alpha less or equal than -1, just make the following change of variables, and you will end up with the same differential equation, and thus the same solution, but with beta instead of alpha. So that's all you have to do. Now, we have also assumed that x is in the range -1 and 1 because we want to use the Frobenius method, and we just want to propose a solution in terms of an infinite series. Polynomials, an infinite series. Now, the first case is if alpha is not an integer. In that case, we can use our gamma function, we have no problems using it, and this would be our solution, an infinite sum of even order polynomials and another infinite sum of odd order polynomials. Now, if alpha is an integer, we end up with, two different solutions. If alpha is even, we end up with this top solution here, which is the sum of all of this, which is just an even order polynomial, a finite order polynomial. And this would be the even Legendre polynomial. This is a kind of a long expression. There are more short expressions for it, but this is the even order polynomials, Legendre polynomials. And also, remember that we have to add this other term, which is, well, the exact same infinite series term. Now, if alpha is odd, and well, assuming that it is not -1, so we don't have any problems, then this will be a solution. In this case, the infinite series is the polynomials with even powers, and the finite series is the one with the odd powers. And just you may say, well, what is this limits here? Well, if alpha is even, we're saying that there is some value of m for which is equal to alpha, and really it should be 2m, because m should be even. So there's some value for which this holds, and if we just isolate it, we see that, well, for that value, m is alpha over 2. So really our series will only go on to this value of m, which is alpha over 2. Likewise here, this finite series will start being 0 whenever we get past this -1 over 2. And this just comes from the fact that we're assuming that alpha is an odd integer. Okay, if we isolate m, we see that for this value of m, well, this will be our last term, because as we saw before, for higher terms, right, for higher odd terms of alpha, all of this will go to 0. So we end up with an infinite even power series and a finite alpha power odd polynomial series. And now, of course, I said that alpha is not -1, so we have to consider the case where alpha is -1 separately. And what all we have to do here is, well, if alpha is -1, we can use this expression, so we just have the same as before for the even terms. And if alpha is -1, we can also use this term, there's no problems here. And if you just calculate it, you see that we end up with 2k plus 2 and 2k plus 1. And as we saw before, this kind of product is just 2n factorial. So we end up with a1 times the infinite sum of 2n factorial over 2n plus 1 times this monomial, x to the 2n plus 1. So yes, that would be the whole solution. You have it here written down. I'm going to erase this just for a minute. And well, I hope you liked the video. It's quite a long video, so if you don't you don't have to watch the whole video. I will separate it into the different parts, and if you just want the answer, just go right here and you can see it. Well, as I said, just one important thing is that the Legendre polynomials, so defined as this, as Pn, are defined by this relation and this other pink relation. These are the even terms of the Legendre polynomials, and these are the odd terms of the Legendre polynomials. I will make more videos about it, I'm talking more in depth, but just to give you a heads up. So well, I hope you liked the video, that you found it interesting, and that it helped you in some way. So well, see you in the next video.